All right, so the second part of these notes, we are going to look at what's called the conservation of momentum. So you're going to be looking at collisions in this section. In the top picture, you've got the red bird flying in, and he's going to hit the ball. And then you can see after they collide, the ball is going to roll off this way, and the bird's going to bounce back. So we need to look at the momentum of each object, the bird and the ball, before the collision and after the collision. And we're going to have different types of collisions that we'll look at. Here you see the bird hitting and bouncing off. Sometimes in car wrecks, the cars collide and they get crumpled together and they slide off. So we'll be looking at a couple different types in this section. If we look at the bird, so here before the collision, his momentum is 3 times 1. So we'll write that up here. So his momentum before is 3. And the ball is not moving, so its momentum is 0. Now if we look at the bird after, his velocity is now -1 and his mass was 1. So -1 is his momentum. And then the ball, its mass is 2. And its velocity is now 2. So that's going to have a momentum of 4. Now, one thing to notice here, the total momentum before, so 3 plus 0 equals 3, and the total momentum after, -1 and 4, also equals 3. So that's something to keep in mind. The total momentum is going to be conserved. It's going to be the same before a collision and after a collision. So momentum, the same before and the same after. We're going to have two types of collisions. The first is elastic, where in those collisions, the momentum is transferred from one object to another. So if we look at these vehicles, we've got the truck and the red car. So if we go ahead and we'll solve the momentum for each one before. So if we've got the truck, his momentum is going to be 10 times 3,000 or 30,000. And the car, velocity is 0, so his momentum is 0. Then we have the car afterwards. It gives us 1,000 and a velocity of 15. So we've got 15,000 there. Well, we said when we looked at the birds that the momentum before has to equal the momentum after. So if the total was 30,000 before, then the total after has to be 30,000. So that means if the car is 15,000, then the truck has to be 15,000 at this point. So you can see that the truck has transferred some of its momentum to the car. So now if we were asked, can you find the velocity for the truck? Yeah, we can do that. So 15,000 divided by the 3,000 mass is going to give us 5 for our velocity for the truck. This says we have railroad car A rolls at a certain speed against car B. So we've got car A moving, railroad car B is at rest, so its momentum is 0. If the collision were perfectly elastic, compare the motion of the cars after. So perfectly elastic means that car A is going to transfer all of its momentum to car B. So whatever momentum, we'll call it X for A, before means that afterwards A is going to be at 0 and B will be at X. Newton's cradles are a fantastic example of elastic collisions. And I will attach this YouTube video on here because it's rather entertaining, soothing to watch. but YouTube won't let me just throw it in here, so I'll attach it. Inelastic collisions, you're going to have the objects collide and then they become entangled. So we have grandma roller skating with the little kid before they're separate, and afterwards she's picked him up. I guess she's a super skater, and they're one unit. So how do we solve these problems? Well, we know that their momentum is going to be equal before and after. So grandma is 80 and her velocity is 6, plus the little boy, his mass is 40 and his velocity is 0. So if we do 80 times 6, our total momentum over here is 480. Afterwards, if she's holding him, they're all one unit, their velocity is going to be the same. So we can do velocity times their masses added together. So if this side equals 480, this side has to equal 480 as well. So if we've got V equals, and that's 120, we can say their new velocity is going to be 480 divided by 120. So their velocity afterwards is 4. If we look at this scenario, we've got a baseball and a catcher, and then they're going to become one afterwards because the ball is going to be in the guy's glove. Again, equal. So the ball before is 0.15 times 45, and his velocity is 0, so we'll just say plus 0. So if we go ahead and 0.15 times 45, this side is 6.75. Afterwards, they're going to have the same velocity, so 0.15 plus 0.25, so the mass of the ball and the mass of the guy. So 6.75 is going to be V times 0.4. So 6.75 divided by 0.4 is going to give us a velocity of 16.875. Now, one thing to watch, and on this one it wouldn't be that big a deal. The ball's moving this way, so if we called the ball positive over here, the motion would be positive on this side as well. Now on this one, it's a little bit different. We've got a cannon and a cannonball. So, well, the cannon and the cannonball are going to start together, right? And they're initially not going to be moving. So the total momentum on this side is going to be 0 because the cannon is not moving and the ball is not moving to start out with. So what happens when the cannon actually shoots off? The ball moves this way really fast, and the cannon may have a little kickback and go backwards, which would mean the velocity here, the cannon, would be negative. So on this side, we'll do cannon and ball. So the mass of the cannon is 96. We don't know the velocity of the cannon. Plus the mass of the ball is 4, and the velocity of the ball is 120. And all of that's going to have to equal 0 because those objects were not moving to begin with. So let's do a little math here. So 96 times velocity. Oops, let's see. So 120 times 4 is going to give me 480. So 480, if we subtract it over, we'd have 480, actually negative 480 equals 96V. So divided by 96. So the velocity of the cannon is going to be negative 5 meters per second. Now you're going to have a formative on Collision Cart Interactive. And again, watch the directions very carefully as you do this. And let me know if you have any questions.